Pamela Harman, directora de Educación e investigadora principal del SETI Instituto.
Yes, we can.
And you see my slides?
Yes.
Okay, and I'm in presentation mode?
And not totally.
How's that?
Try again. Perfect.
Okay. There we go. All right, so thank you for having me. My session is entitled Detecting Visible and Invisible Light in the Classroom. And then I had to add the virtual classroom because that's what we're doing these days, and also in space. That's really why we're here today. And all right, so the agenda, I'm going to provide an introduction to infrared astronomy, especially as applicable to astrobiology. Then I have some classroom activities that work in person, and as you will see, they work in the virtual classroom as well, or virtual presentations. So why detect light? Astronomy relies almost entirely on the analysis of light to learn about our universe. We get a better understanding of the universe by looking in space using detectors for light, energy, or radiation invisible to our eyes. Different energies of light reveal many secrets about the lives and composition of objects that are otherwise hidden from us. By detecting and analyzing the light emitted by an object in space, astronomers can learn about its distance, motion, temperature, density, and chemical composition. Since the light from an object takes time to reach us, it also brings us information about the evolution and history of the universe. So if you think about the cosmic microwave background study, which really helped us determine the age of the universe, that was determined by using invisible light, the microwave wavelength. So I'm going to focus on infrared light, which was discovered by Sir William Herschel in 1800, just 220 years ago. And I like to think that his sister Caroline was there and had a big part in this as well. So what he did was he wanted to determine if there was a different energy level in the different portions of the visible spectrum by using thermometers. And he placed one thermometer outside the spectrum as control. And when that thermometer temperature also went up, then he had discovered invisible light, infrared radiation. And just for a quick review, for the because some of you are teachers, I think, the EM spectrum, there's light all around us. Just this small portion here in the middle is the visible spectrum that's detectable by our eyes. You know, we want to think of our eyes as detectors, and that translates to the detectors in telescopes. So all around us is all this light happening, but we don't see it. It's invisible. And infrared is next to the visible spectrum, and you can see it's a pretty wide range, and we divide that into near infrared, mid infrared, and far infrared. So what are the challenges around using infrared light in astronomy? Earth's atmospheric water vapor, the moisture around us, absorbs almost all the incoming infrared radiation. Even mountaintop observatories get a very limited view of the infrared universe. So what does this mean? So here's a chart that shows opacity versus wavelength. So the further down the light travels, it's transparent. So we see right here in the visual window, our atmosphere is transparent. We can see, we can detect it. Over here in the radio window, we can detect radio wavelengths. So the atmosphere is transparent, but up here in some of the higher wavelengths, you see that it's opaque, and that's a good thing. We don't want gamma rays reaching us down here on the surface. And for the large part, not completely, we're protected by the atmosphere from ultraviolet, because you can see it does not reach us. It's only opaque up to this point. And then long wave is also, most of it does not reach Earth. So what do we do? observations at some wavelengths are difficult or impossible from Earth's surface, as I just showed you. So what we do is we can have ground-based observatories, we can have aircraft-based observatories, and spacecraft-based observatories. So if this is the penetration through the atmosphere, you can see we have to get some observatories up here in space, and we can have an observatory on an aircraft and to detect infrared light. So we can have ground-based for the visible, a little bit of infrared, and we can have ground-based over here in radio wavelength. So infrared telescopes detect objects that are cooler than stars, and this is really cool, if you will, for astrobiology, because we can study planetary atmospheres, polycyclic aromatic hydrocarbons, or PAHs for short, which are the building blocks of organic molecules. We can study chemistry of the interstellar medium, young stellar objects that might someday form planetary systems, cometary molecules, and complex molecules that are always cooler than the stars that they're around. Ground-based observatory, here's a couple of examples. The Visible and Infrared Survey Telescope of Astronomy, VISTA for short, is in the Paranal Observatory in Chile. NASA has the Infrared Telescope Facility, the IRTF, in Hawaii, and there's the IRTF there. Aircraft-based. I've had the pleasure of being on board SOFIA, the Stratospheric Observatory for Infrared Astronomy. You'll see it's a 747 airplane with a hole cut in the side for an infrared telescope. This photograph was taken during the day, but of course it's an infrared telescope, so it only flies at night. Its predecessor was the Kuiper Airborne Observatory, also known as the KAO. And then when we think of space-based telescopes, Hubble, of course, takes all those beautiful visible light images, but it also works a little bit in infrared. The James Webb Telescope, which is scheduled to launch in October, and this is an artist's rendering on the right, not a photograph, will work in infrared. And JAXA, the Japanese space agency, had a space-mounted telescope called Akari. And these are just a few of the dozens of past operating and planned infrared telescopes. So here's the difference in transmission of what you could see Mauna Kea, which is it's almost 4,000 meters at the top of Mauna Kea, versus what SOFIA sees flying at over 13,000 meters. And then, of course, spacecraft-mounted observatories are well over 500 kilometers from the surface of the Earth. So you can see that, out in this wavelength, you're just blind with your telescope. But if you get the telescope up higher, you're going to get more infrared imaging and data that you can use in spectroscopy, of course. The multi-wavelength astronomy is really important to astrophysics and astrobiology. Any object can appear radically different depending on the type of light that's observed from it. So this is a portion of the night sky around or the constellation Orion, and I apologize for being northern hemisphere centric, versus infrared. And so we wouldn't see these big energy areas of infrared light if we didn't use an infrared telescope. So this tells us there's so much more going on in this area of the night sky versus the visible image. So here's the question you might get from your students. Well, if it's invisible light, how did we make a picture? Well, this is what we do. We use representational color. And graphic artists work with the scientists to assign values. So here's a baseball stadium, or think of a soccer stadium, where the color coding tells you the price of the seats. So in this area, the red zone, those are the most expensive seats at this baseball stadium because they're near home plate. In a soccer field, the most expensive seats might be near the goal. Then, so translated over here in this radio energy map, red is the most intense. And so what this is mapping is a single wavelength, and there's the most intensity at the red, and the violet is the weakest. So like this is the most expensive, and these are the less expensive. We go intensity, greatest to highest. And so that's how we take infrared data and create image. We assign color values and make a picture. So in infrared astronomy, there's imaging, spectroscopy, and spectroscopic images. You may not recognize this image, but this is Jupiter. And this is actually this was the first light image captured with one of the SOFIA instruments. And if we didn't study Jupiter in infrared, we would not see this white band. And this white band is intensity in infrared. And we were able to calculate that this energy level was higher than the energy level that could have been produced by its proximity to the sun. So scientists have figured out that there's something welling in here going up and down. So there's energy there that we wouldn't have seen otherwise. Over on the right, that is an infrared image of the center of the Milky Way galaxy. There's a black hole at the center of our galaxy. What we see here is infrared energy swirling around the center of that black hole, which helps us find it. We're still really curious, why is there this concentration of infrared light, in that position? So for everything that we find, we generate more questions, and that's what science is all about. Now, in order to generate that image of Jupiter, it was actually captured 3 images at 3 different wavelengths. And then you assign a color value, and then you stack them. And that happens much like visible wavelength imagery. You capture images at different wavelengths and stack them up. So these 3 images were stacked up to give us that image. Here's a helix nebula in visible and near infrared. And so in the visible image on the left, we see the hot gases. And in the infrared image on the right, we see the dust that is cooler than the hot gases in that nebula. And so this cooler dust is really interesting to us as we study astrobiology and want to know how planets form, how atmospheres form, and then we want to know more about the chemistry and the biochemistry. So there are spectrographs and spectroscopes also involved in infrared astronomy. And just a quick reminder that a hot gas through a prism or a grating will give a continuous spectrum, or a hot light, a lot of light, white light. But a hot gas is going to emit light only in certain bands, and we call that the emission spectrum. And then if you have light passing through a cold gas and then through either a prism or a spectrum, we get the absorption lines. And these, of course, are complements of each other. This is the gas emitting, and this is the gas absorbing the light that passes through it. So recall that spectrographs or spectroscopes have a slit at one end and a dispersive element at the other. We also often use holographic grating in the classroom. In an instrument, the element can be a prism, a grating of some sort, or a grism, which is a grating on top of a prism. So that produces a picture of the entrance slit at each wavelength. So here would be the slit, and here's a picture at each wavelength of red, each wavelength of yellow. And here's the picture, but there's no light at this wavelength, so there's no picture. Here, there's light, but here it's absorbed. So that's how we get a continuous spectrum versus an absorption or emission line spectrum. I'm showing you this in the visible wavelength, but of course they do the same thing in infrared. And that's how they confirmed atomic oxygen on Mars. So there's a spectral line curve of atomic oxygen that was found on Mars. And then you may have heard recently in the news about water found on the moon. Of course, we had found water on the moon earlier, but recently, using SOFIA, astronomers were able to find the presence of water in areas that were illuminated by the sun. So this was the new exciting finding. We'd found water ice in shaded areas, but this was in the sun. And what was really interesting is these molecules are encased. They might be encased in micrometeorite material. So, and there's a couple other ideas. And there's not a lot of water. There's about 12 ounces, estimated 12 ounces per cubic yard, which is just a little smaller than a cubic meter. It sounds like a lot, but the Sahara Desert is 100 times more moist than that. So the Sahara Desert has more water than per cubic meter than we estimate on per cubic meter on the moon. However, this is still exciting news because there's water there, and this is going to inform some of the processes and steps and ideas for the human exploration mission Artemis, taking us back to the moon. This is an artist rendering of two debris disks encircling a star, and this star is 40 times the size of our sun. But what was interesting with spectroscopy, researchers found molecules in the debris disk, in between these debris disks, that are the building blocks for life as we know it. Water, ammonia, methane, all important for, the origin and evolution of life. And now, so I mentioned a spectral image. So here's a star field. And then when you use a GRISM, you actually get spectrum from these point sources. And those spectra then can be analyzed. And it tells a different story than looking at the point source. And then lastly, wow, Sophia has an instrument called HAWK Plus, and it's a polarimeter. And what it does is it detects the polarization of the light. So think of light passing through dust that's elongated, long particles of dust. And so you know that the light can only pass through these long particles this way. If the dust is going this, the light can't pass that way, it can only pass one way. So they can line up the light waves and know its orientation and therefore its field. And so in this is a Spitzer image, another spacecraft mounted infrared telescope in the Rho Ophi region. And in the central region of this area is a star forming region, and some of these stars will probably form planetary systems like our sun. And using the HAWK instrument, researchers are able to finally observe the systematic variations of far infrared polarization in a spectrum that exists within an interstellar crowd. So so if you think that the dust is disarrayed in this area, this artist interpretation of the data shows us that this dust has orientation, there's magnetic fields, there's polarization. And so this is really going to inform us in the understanding stellar and planetary system formation. Okay, so that was a quick review of introduction to infrared astronomy and as it applies to astrobiology. And so how can we take this to the classroom so we can show students some really cool pictures and we can show them some spectra, but what does that mean and where do you start? So when in a classroom, we always want to start with the EM spectrum like I did. Remember that the visible light is a small range, but this light is around us and we use it all the time. Humans exploit the EM spectrum. We use it in communication. We use it to cook our food. If your students think that the little light bulb in the microwave is cooking the food, here's the test. Take a frozen dinner, shine a light bulb on it and see if it gets hot, and it won't. So there's got to be light in that microwave that we can't see. And we use infrared energy to heat our homes. We know we have ultraviolet light in fluorescent tubes, but we have to protect our eyes and our skin from it. And we use X-ray and gamma ray in healthcare. So it's around us and we use it. In astronomy, multi-wavelength images tell us a bigger story, more of the picture. So here's the Milky Way galaxy in some long wavelengths up here, different particular wavelengths in radio, infrared, mid-infrared, near-infrared, and then optical, and then in some higher energy in X-ray and gamma ray. And we need all of this data to fully understand cosmic origins and formation of planetary systems. Okay, so I am going to stop sharing so that I can show you some activities. And Okay, so can you see what's on my table here?
I can see your dashboard.
You see my desktop. Okay, I need, how about if, right. Okay, my share screen is off. Can you turn, so I need who's ever controlling to turn my camera on. Is there a way to do that?
Okay.
I need my camera back on.
They can see your desktop.
No, this desktop, not, can you access my camera? Thank you for your patience. I'm doing something a little
It's
extra.
okay, Pamela. Don't worry.
Yeah.
I can.
¿Alguna vez
No.
te has preguntado
Your screen is
cuáles
black.
fueron los elementos esenciales para la vida formados en las estrellas? ¿Cómo se forman los planetas rocosos como la Tierra y cómo se adquieren los compuestos volátiles como el agua? ¿Cómo surgió la primera forma de vida celular en la Tierra? ¿Qué papel juegan los minerales en el origen de la vida? ¿Quién puede obtener esa respuesta? La astrobiología. En nuestro país está el Instituto de Astrobiología de Colombia, IAC, y buscamos promover y generar divulgación, educación e investigación científica para crear una cultura fundamentada en la ciencia. Nuestros cursos, talleres y salidas de campo están diseñados para estudiantes, profesores e investigadores que quieren ampliar sus conocimientos en esta apasionante ciencia. Porque la vida no tiene fronteras en el universo. Para más información, visita nuestra página web www.astrobiología.org.
¿Fue el Big Bang el origen del universo conocido? ¿Cómo se formó la Vía Láctea y el Sistema Solar? ¿Cómo se originó, evolucionó y distribuyó la vida en la Tierra? ¿Cómo imaginas una forma de vida extraterrestre? Si alguna vez te has hecho estas y otras preguntas similares, entonces eres parte de la astrobiología, ciencia interdisciplinaria que está en constante búsqueda de esas respuestas. Por ello, el quinto Congreso Internacional de Astrobiología sigue adelante y ahora será online, del 11 al 14 de noviembre de 2020. Allí estarás junto a astrobiólogas y astrobiólogos del planeta Tierra. Organizan Universidad del Atlántico y el Instituto de Astrobiología de Colombia. Apoyan Gobernación del Atlántico y Grupo de Educación de Minambiente. Porque la vida no tiene fronteras en el universo.
Somos biodiversidad. Somos ambiente. Somos protección a las especies. Somos sostenibilidad. Somos parte de ti. Y tú, parte de nosotros. Somos tu autoridad ambiental. Trabajamos por mejorar la calidad de vida de los atlanticenses. Somos la Corporación Autónoma Regional del Atlántico, CRA.
Respira un nuevo aire para el Atlántico, CRA.
And so the first activity that you can do is with filters and LEDs. These are just little 5mm LED lights and coin batteries. They're relatively inexpensive. And then these are, this is a blue, green, and red filter. I just made them with cellophane or gel. And so you're going to ask your students to make a prediction. What do we define a filter? So if you ask your students what a filter is, they might say it's something you use on Instagram to make your face look pretty, or it's a coffee filter that traps the ground. So what's important is that they understand that a filter is the color of the filter that it transmits. So a blue filter transmits blue light. Okay, the green filter transmits green light, and the red filter transmits red light. Now you're going to ask your students to make a prediction. Here I have a blue light. What are we going to see when we try to look at blue light through a blue filter? So we see that. What are we going to see when we look through green? And what are we going to see when we look through red? How would we explain that? So then we can take a red light, and what do we see through a blue filter? Green. Oh, that's interesting. And then red light through a red filter. And then ask your students to make a prediction. What are we going to see when we look at a green light through a blue filter, through a green filter, through a red filter? And you would ask your students to use the terms emit, absorb, and transmit, and they can draw their explanation, and we want them to talk about this in wavelengths. And as you saw, filters have a role in astronomy, and I'll elaborate on that role in astronomy shortly. All right, so I'm gonna move this out of the way. And so then, so we can use filters to isolate the wavelength that we're interested in. And then, so I went to imaging. So then so I went straight to imaging. Okay, and so, here's an infrared camera that plugs into a phone, and these are $200 to $250 US, which isn't too bad. And you'll notice that it's a color image here, and what you see here is the camera on the top of my screen that's emitting heat, and then here's part of my laptop that's emitting heat. And what's really cool about infrared, remember I said that it doesn't, so when I cover the camera with black plastic, you can still see the image. It doesn't change. So the infrared light is passing right through this black plastic. Now, conversely, I'm going to take a piece of plastic or glass, like a window that's transparent in the opaque, but when I put it in front of the camera, it's opaque. So that's why Sophia and the Kuiper Airborne Observatory have to have a door, a hatch, and not a window, because if we put a window on it, we would get no infrared data. This is another style of camera. These are about $400, and you notice that I have a black and white image. There's advantages to using black and white for infrared because it just shows intensities. The learners aren't focused on what does the color mean, we're just looking at intensity. So I kind of prefer black and white, but these small cameras are color only. So that's just a little bit about imaging. And then there's other way. And then, so now we're going to look at a couple of detectors. If you have your smartphone around or a flip phone, let's see, flip phone, and a remote control. Remember I said we used infrared around us and in communications. So everybody's got a remote control at home that controls something. So if you point it, you're not going to be able to see this as well. But when you look at these, when I look at this in my eye, I don't see any light because it's infrared and my eye does not detect that. However, the selfie camera will detect it, and it depends on your camera, your phone and your camera. Now, fortunately, laptop cameras and web cameras are sensitive in the near infrared. So we know they're sensitive in the visible wavelength, and they're also sensitive in a wavelength just near it. So you can see that flashing, but when you look at those in person, you can't see them. And you can have your students test the lenses on their smartphones or flip phones. Flip phones work really well for this. And some of the lenses don't detect infrared because because they put money into making those lenses better. So the selfie lens is usually the better choice. Now there's another way to detect infrared light. And you can build a detector with just a little speaker. Here's a little speaker and a solar cell. And we know that, again, that solar cells are sensitive to visible light because that's what they're built and designed for. But we have also found that they detect near infrared. Now we have to break up. We have to break up the signal. That's why. Okay. I'm going to turn my volume up. All right, you may want to turn your volume up. I've got mine up. As far as it'll go. And the reason that we have to interrupt the light is the speaker needs a change in voltage to move the magnets. The magnets move, and then that moves the diaphragm that makes the concussive wave that we can hear. So I'm going to use my remote controls. So hopefully you're hearing that signal. So so we can use light as a signal, and obviously because there's a different sound, we know that there's different intensities, there's different frequencies to the infrared light. So here's another, so that's another way to detect infrared light. So after these demonstrations, you ask your students to do a claim of evidence reasoning exercise, and you ask the question, is there light in that we can't see? Is there invisible light? And so they need to make a claim, and hopefully after these demonstrations they would say yes, and their evidence would be the detection by the detector circuit, the using a smartphone, or using the camera. So that's the evidence. And then the reasoning is these devices are designed to detect light. They're not detecting water, they're not detecting sand, they're not detecting the presence of the Arctic wolf. So they wrap that package in and demonstrate that they understand that there is light that we can't detect. So I want to go to spectroscopy, and this is, okay, all right, so Brian was going to turn the lights off, and okay. And so what I have is I have a clear bulb, and it's on a cord with a rheostat so that I can change the temperature. And then I have, I have a box with a slit in it. So remember, you need a slit and you need a holographic grating. And I'm going to put a holographic grating slide on the lens of the camera. All right, so now I have that, and this is going to, okay, so this. All right, so I see a spectrum in the upper right-hand corner. Oh, where's, well, this. Ah, okay, look over over my shoulder. There is a pretty good spectrum. And the brighter I get, the fuller it gets. You'll see the blue and the green. Now, if I use the rheostat and I take the temperature down, we're going to lose the blue and the green. And so there's a correlation between temperature and color. So you can see that. And as I turn it up, and it's off my shoulder, if you can see that, and the brighter it gets. So this is how, so we can use spectroscopy to demonstrate the relationship between color and temperature. Okay, now if you want to talk about spectral lines, and you're in your home situation, a good old, let's see, compact fluorescent light bulb. This is mercury vapor. So it is going to show the emission lines of mercury vapor. And you can do this at home. If you have emission tubes and power sources at your classroom, you can do what I'm doing so that your students can see spectral lines at home. Okay. I think you can sort of see it. If I didn't have my PowerPoint, slide on open, you would see it better. Let me move it around just a little. Ah. All right. Okay, thank you, Brian. And if you'll turn the light back on. Uh-oh. Okay, there we go. Okay. Okay, so I hope that the spectral lines was probably the hardest to see, but it does work. You just have to get the camera and the box at the right angle, and you would have seen the spectral lines of mercury vapor. And again, if you have emission tubes and power supplies, you can do that, obviously, in the virtual world. And I apologize for not having full control of my camera, but I think you got the idea. So here's a slide showing the results of what I showed you, looking at the LEDs through the different filters. And there's some anomalies in there. And we're going to, and those are always the interesting lessons. So here's a picture of a filter wheel from an infrared telescope instrument. So this wheel is in the instrument, and there's a computer command signal to spin it to the filter that the astronomers want to use. They want to collect light at a certain wavelength, and they actually use filters and wheels in their instruments. This is more on imaging. This is 2 pictures that I myself took. I want to assure you that the plastic garbage bag was draped in front of the toaster and was not over the toaster. I did not start a fire that day. But this is an example of the image, the importance of multi-wavelength astronomy. You could ask your students to what this image is, and they could probably guess a toaster. And so when we look at humans, which we are looking at humans in infrared a lot now, because it is one way to take temperatures and make sure that nobody's running a temperature during the COVID pandemic. This is a person. You'll notice that the infrared light does not transmit through the glasses. Once again, that's why Sophia has a door and not a hatch. And here's an image of a person in black and white. Again, I think this is the better medium. Just like I showed you with the black plastic over the camera lens, this person has their hand in a piece of black plastic, and we can see right through it. Here we see that there's intensity here around the eyes, the nose is cold, there's intensity around the neck, similarly here. You can make serial spectrometers. You just need one of these holographic grating lenses, and you can buy them online. And at the opposite end on the serial box, you make a slit, and trim it up with some black tape, and you've got a spectrometer. So once you see one emission spectra, like demonstrating the mercury vapor spectrum, there are emission spectra of the elements online, either in emission or absorption. And so there's lots of resources there. So once you see one, you understand it, and then you just use the resources. Now, so those anomalies that we saw looking at light through the filters, these are the response curves for those filter materials. These are GAM filter products. And the fact that we could see some red light through a green filter, that's depicted here in this light curve. And with advanced students, you can have them look through a spectroscope through a filter at a light, and they'll see an incomplete spectrum, and they could map this out themselves. Even in filters that are used in astronomy, it might be like a 27 micron, but that would be the peak, and it's going to let light in on either side of that specific wavelength. So this is useful information to astrophysicists as well. So there's more images and animations at coolcosmos.ipac.caltech.edu. The images I've used are NASA images or my own or other images in the public domain. There's a lot of classroom resources available here. And so I'm going to say thank you, and I'll take questions. And my home institute website is SETI.org, and there's a lot of information about the institute, about our scientists, our research, and the people that work at the institute. Thank you.
Thank you so much, Pamela. And the audience is very, very excited with your virtual lab demonstration. It's great. I have, in the social media, we have some questions. Can you hear me?
Yes, I can. Go ahead.
Okay. The first question, in this time with the COVID situation, when children cannot go to the school, how can they have science activities at home with parents, with teachers, like you did today in your presentation? What is your recommendation or some tips for work at home?
So I think that you can do those, you know, the color filter activity. You can do that at home, and there's a lot of activities online. And I know that online isn't the answer for everyone, but if we go backwards and we say, what is science? Science is curiosity and asking questions, and we can go outside and ask questions ponder questions about what's going on about us, and try to answer those questions and come up with tests to answer those questions. So it might not be astronomy, but you go out and you wonder, well, why is this plant growing better here than over here? Is it soil? Is it water? Is it the sun? So you could test that. You could add water. You could cover the plant up with a box and see if it grows without sun. So, and reading about the history of science, find out what other people have done, find out what other people, how they got motivated to be scientists, how they got motivated to be an engineer. You know, by training, I'm an engineer, and that's because I like to tinker. You know, I like to take things apart and then try to put them back together. I'm not always as successful with that. And go out and look at the night sky. If you're in an urban environment, you can still see the planets. And you can still see bright stars, and observe the movement. Go out and find them night after night. Where are they? Where'd they go? Why are they moving? Try to explain that using the relationship of the Earth and the Sun and the star and those planets. Go out and observe the moon. Where is the moon? What time is the moon up? What shape is it? Keep a journal. I think, you know, one way to be a scientist at home is to make observations outside every day and keep a journal and write down the things that you wonder about.
Thank you, Pamela. Give me one moment to translate. Doctora Pamela nos dice que la ciencia es motivación, los niños tienen mucha creatividad y en casa se puede explorar el mundo. Desde sus ventanas pueden ver el cielo, pueden ver las estrellas, pueden cuestionarse sobre los movimientos lunares y prácticamente pueden hacerlo en casa. Obviamente pues pueden apoyarse con material que encuentran en línea y pueden hacerlo con el apoyo de sus padres y también pues de sus maestros. The next question. What are the main difficulties to have a scientific curriculum in a traditional school, and the possible solution according to your experience?
Well, that's a very good question. And one of the reasons that I'm at the SETI Institute in the Center for Education is I believe that teacher training, teacher professional development in the areas of science and engineering is critical to improving science education. I did teach science and math. I've been an engineer and I've been a math and science teacher. And I was so lucky to work with teachers that believed in inquiry-based learning. You learn science by doing science. And the more teachers that teach science that way, the better we all are. The more opportunities that students have to be engineers, to just, even if they're just building something out of paper or spaghetti and gumdrops, and go through the iterative process. So say you're trying to make a bridge out of spaghetti and gumdrops, and you learn every time you remake it, you improve it, and that's engineering. So I think teacher professional development is most important because each teacher reaches hundreds of students. So an event like today, you know, you're trying to improve science education.
Yes, maybe the question is because, you know, maybe you remember when you visit Colombia, in our protocols, in our curriculums, we don't have the science like a priority. Is not our priority. For example, the traditional schools is sometimes historical arts, but the science is a complement, not the priority. Yes, and it's necessary to change that.
It is necessary to change it. In fact, you know, in the United States, there's more testing in English language skills and math than science. So what science teachers have done is, you're going to work with the English and the math teachers. You're going to write about your science project. You're going to write about a scientist and the math, and then work with the math teachers and say, well, there's math in this science project. There's math in this experiment. I want you to have them to do the math in the math class. So it also takes coordination to, you know, with other teachers.
Maybe it's necessary to change the political rules, in your opinion, first, or is difficult?
It is certainly difficult because the school districts, you know, have to, they have the rules, and the teachers have to go by the rules of the school district. And so there has to be some top-down pressure, you know, at the high level, and then there's bottom-up pressure from the parents of students who want their students to know more. So they kind of meet in the middle if you have both pressures. And just, I'll say that, you know, STEM careers are good for the economy everywhere.
Yes, in special for South America countries, for example, Colombia, in continued development. Doctora Pamela menciona que realmente en esta última parte, presionar por políticas para que cambien los sistemas de educación es un poco difícil, y ese cambio pues empieza precisamente en nosotros, en el aula, en el caso de los docentes, en casa con los padres, y a partir de allí ese cambio se puede dar. Esas dificultades para crear un currículo, creo que todos los profesores la han vivido. Cada escuela, en especial las escuelas públicas, dependen de una línea establecida. De pronto las privadas tienen esa flexibilidad y es lo que se busca pues con carreras STEM, que a la larga le van a servir más a una nación como Colombia. Okay, the last question. How to motivate the girls, for example, in Colombia, to join in science, and how to combat gender discrimination that sometimes occurs in the classroom. And in Colombia, we have a lot of problems with the girls in the education.
That's a really good question, because you know, my gray hair probably gives you a clue, you know, that I'm not 29 anymore. And so when I was in engineering school, you know, it was tough. I was one of the, you know, first women through my department at university. And so, you know, what I would have liked to have had was more mentorship. And so those of us who have gone through, you know, we need to look back and, you know, be willing to band together and support women when they get into higher ed. At the kindergarten through 12, you know, elementary, middle, and high school, again, I think there's teacher professional development. There are skills that can be learned on how to, you know, better incorporate young women into the STEM projects, into STEM class, and into STEM math. And we do know and we do understand that girls are curious and tinkerers, and then they reach an age where what the boys think matters. And so, you know, that's, you know, we have to get over that. And there's some research that shows that putting girls in the putting girls into the small collaborative learning groups instead of mixed groups where they can, you know, talk to each other and, you know, continue on in the math and science. So there's teacher skills, teacher skills, there's mentorship. And then I think a really important message is that we need women. Women are 51% of the population. And if women aren't involved in the decision-making process, if they're not involved in the thought process, we're missing out. And women are excellent collaborators. Women are excellent at science. They're excellent at math. Those are skills that everybody learns. We're not born, you know, being able to do calculus. So we're capable of learning, and women bring another perspective. So in those fields, you're needed. We want you.
Thank you, Pamela. Pamela nos está diciendo que los profesores, los mentores deben de tener claros sus lineamientos, donde siempre se deban de incluir las mujeres, las niñas en cualquier actividad. Ella menciona que son capaces, igual que cualquier otra persona, cualquier niño. Siempre debemos de mantener ese equilibrio y evitar esa discriminación en el aula. Que quizás a veces se considera que las matemáticas son aburridas para ellos. No, no lo es. Ellas pueden hacerlo como cualquier otra persona, repito. Y esa discriminación hay que combatirla precisamente con ese equilibrio. Y las carreras STEM pues brindan esa posibilidad, y la ciencia es para todos. Es realmente la esencia que ella nos está planteando. Y pues lo que se busca es que en países como Colombia esto empiece a cambiar, ya que tenemos muchos problemas. Pamela, thank you so much for sharing with us your knowledge. Thanks a lot. I hope the next time you can visit again Colombia.
It would be, I can't wait. I'm eager to come and visit again, and I hope to see and meet many of you in person someday.
Thank you so much. Welcome to the Astrobiology in Colombia. Bye-bye.